Behind me is a problem from the United States of America Mathematical Olympiad. USAMO is the first problem, 2018. And this is the statement. We have positive real numbers a, b, and c such that this equality holds, and you want to prove this inequality. Now, USAMO, it's a very difficult competition. Problem 1 is already hard enough. It's already very hard, trust me. However, this one, for me, felt a little bit underwhelming. A bit less underwhelming than expected. Nonetheless, I think it's a very cool problem, so let's delve right into it. Okay, so first of all, this minimum function is pretty annoying, right? But don't worry, we can just say we'll log, so without loss of generality, we will assume a is greater or equal to b, greater or equal to c. And then, well, this minimum function is of no use anymore. It's overkill, so we can just replace that with 4c squared, basically giving us the minimum of whichever one of those three we had, right? Okay, what do we do from here? Well, notice that we have the sum of squares. And over here, we have a cyclic sum of a, b, and c, right? Well, whenever you see that, it's probably a good idea to consider completing the square over here on this side, because notice that if you were to add 2ab plus 2bc plus 2ac on both sides, so basically we change the coefficients over here to 4, right? Because we're adding it on both sides. So this becomes 4, this becomes 4, and this becomes 4. Now, notice that this, when we add it to this side, this part becomes a plus b plus c squared, right? This side becomes this, right? It's a factored form. Notice that the original inequality, I'm just going to rewrite it because it looks kind of messy, like from here, right? So the original inequality becomes 4ab plus 4bc plus c squared. But remember, a plus b plus c, we have this. So let's just get it over with. Let us replace it with 4 cube root of a, b, c. Okay, now we want to prove that this expression is greater or equal to this expression. How do we proceed? Well, I'm going to introduce a new concept. And even though this concept might seem new to many of you, it's actually a very well-known concept in Math Olympiads, especially for the USAMO. It's the concept of homogeneous inequalities. Here's what I mean. So, suppose that this inequality is satisfied for some choice of a, b, and c, okay? Now, consider this. If you were to take each of a, b, and c and scale it by some factor f, where f is positive, so if you were to scale a, b, c by the factor f, and then you substitute a with fa, b with fb, and c with fc, right, sub it into this inequality, you will notice that it is possible to cancel out an f squared on both sides of the inequality. And when you cancel those f squares out, you will realize that the inequality looks no different from if you just plugged in a, b, and c. Now, what does that mean? Well, it means that if this inequality holds for some choice of a, b, and c, then it must also hold for any scaled version of a, b, and c as well. Now, in particular, this would actually mean that we can, without loss of generality, set a plus b plus c equal to 1. And the reason is because if this inequality holds for sets of real numbers summing to 1, positive real numbers, of course, if it holds for this condition, then it must also hold for sets of positive real numbers not summing to 1. You can scale each of a, b, and c by some common factor, and, well, it can sum to other values as well. So this is indeed a without loss of generality. Okay, where can we apply this equation? Well, notice that for this side, we can write it as 4ab plus 4c times b plus a plus c, and then on this side, it would just be 1, right? And notice that, well, this over here, that's just 1. So the inequality further becomes 4ab plus 4c is greater or equal to 1. So all we need to show is this very simple looking inequality. How do we do that? Well, I'm going to have to introduce a well-known inequality that's also very widely applied in inequality proofs. It's the AMGM inequality. Very famous inequality. It basically states that for positive real numbers x and y, then we have x plus y over 2 is greater or equal to square root of xy. And notice that this can be rearranged into x plus y greater or equal to 2 root xy. So both of these, 1 and 2, are equivalent statements. These are saying the same things, and they're both true. It's a well-known fact. So we can use this to prove this inequality. Notice that by AMGM, 4ab plus 4c is greater or equal to 2 times the square root of 4ab times 4c. This side would be equal to 8 times the square root of abc. And remember, we have a plus b plus c is equal to 1. And from this equation, we can easily get that ABC must be equal to 1 over 64, right? So this side becomes 8 times root of 1 over 64. It's 1. Perfect. So this expression is indeed greater or equal to 1. Proved. We're done. As you can see, if you know the right things, it's kind of underwhelming, right? However, nevertheless, very great problem, very nice and elegant solution, especially for people who are just, starting with Olympiads. So yeah, I hope you enjoyed this video. Always remember, homogeneous inequalities, very nice, and also completing the squares whenever you see something like, sum of squares, that's also a very good technique. So yeah, I hope you enjoyed this video. If you did, then please consider dropping a like and subscribing. Thank you very much. Bye.